Fine. So we'll start with Boolean algebra. So in that actually I'll cover the logic gates first. Now in this logic gates, right? Okay, so I think it should be available. Let me check it. So in case if it is not available, okay, I will update you on by tomorrow, I think. Okay, yeah. See this. So in the Boolean algebra, right? So first of all, actually we need to understand what is this statement of Boolean algebra. So the thing is, when we design the logic gates we means if you wanted to implement any particular processor, right? So the methodology what we are going to adapt is the Boolean algebra. So there actually we wanted to design. So with the help of binary system, so what we are doing is, so we need some system where you will be giving certain inputs and then you are expecting certain output. Now actually with these inputs, you have defined the functionality such that suppose if I give 0 here and 0 here and 0 here, 0 here, then you might expect 1 here and you might expect 0 here, you might expect 1 here. Now actually suppose if the operations are 1, 1, 1, 1, then actually you might expect 1 here, 0 maybe here. Now this is the required functionality and these are the inputs, that's what you are giving. Now keeping this in mind, you have to design this system. So you need to design this system so that if I give this kind of inputs, this kind of output should come. So this is the problem statement of a digital design engineer. Now for this actually the methodology what we are going to design here it is, see these are the inputs. Let us say I have this is x, y, z, w. Let us say these are the 4 different variables. Then this function whatever I am expecting here, let us say this is p equal to f of x, y, z, p, z, w. So for these inputs, you are expecting this output. Now mathematically I can express this as p equal to f of x, y, z, w. Now if you wanted to expect this, now actually you have to filter all these inputs or you have to go through all these inputs and then try to establish this functionality whatever you are expecting. Now this functionality can be achieved by adopting logic gates inside. So you will be using these logic gates to design this functionality so that if you give this input, you can get this output with the help of these logic gates. Because logic gates operates only on the Boolean. Boolean meaning, so either true or false. So this is what meant by Boolean, either true or false. That means you have got only 2 options. You might get true, you might get false. For the inputs, if it is false and this is false and this is true, and this is false and this is true. For this kind of inputs, you are expecting this kind of output with the help of these logic gates. Now actually, as you are expecting this functionality with the help of these logic gates, you need to understand what is this logic gate at all. And you need to understand how you are going to achieve this functionality with the help of these logic gates. This is the problem statement of a digital design engineer. Got it? So now actually this digital design engineer actually, as he is designing all these things, now let me go through one by one what are all the different kinds of Boolean logic gates that are available so that you can make use of those gates to design this functionality. Got it? So those are, the first and foremost is AND gate. And this AND gate actually, so we will discuss for 2 different inputs. That AND gate may be any number of inputs. So let me consider only 2 different inputs where if you give 2 different inputs, so this is the kind of functionality what I am designing here. So this is A and this is B and you are expecting an output of C which is a function of A comma B, and this functionality should be such that if I give 0 here and 0 here, then I am expecting here as 0. So this is the output C. And if I give 0 and 1 here, I am expecting the functionality of 0. And if I give 1 comma 0, then actually here again it is 0. And if I give 1 comma 1, then actually this is the output that is expected. Now, if a gate is designed in such a way that if it is giving this kind of output for this kind of input, then we named this as the AND gate. So this is the AND gate. And the logic symbol of this gate is, so this is how actually you represent an AND gate. So this is the output. Usually it is represented as Y, and this is A, and this is B. So here actually we can call this as Y. So this is the standard convention. So this is how you can design, or this is actually the basic building block, I can say. Basic building block, why we say is, this logic design, whatever we have designed, right? So you are making use of this AND gate for the designing purpose of this bigger circuit. But this gate itself contains lot of transistors in it. So this internally contains MOSFETs and transistors. So this itself is a very big subject, and these MOSFETs and transistors are used to design this functionality. So for the digital design engineer, this is a black box, and if you give these kind of inputs, this is the expected output. That's what is the information given to the digital design engineer. So that information is this truth table. Got it? So in an AND gate, if you notice, if all are 1, then only you will get an output of 1. For any other case, it is always 0. Suppose if there are 3 different inputs, A, B, C, and the output is Y, so then actually the different values, what we are going to give it here, it is 0, 0, 0, and this is 0, and 0, 0, 1, this is 0, and 0, 1, 0, this is 0, and 0, 1, 1, this is again 0, and 1, 0, 0, this is again 0, and then 1, 0, 1, this is 0, 1, 1, 0, this is again 0, and 1, 1, 1, this is the only place where you can get 1. So this is the basic behavior of an AND gate. Got it? So this is how actually an AND gate is designed with the help of the transistors, and this is the building block where you can make use to design the bigger circuits. Like this, there are many other circuits. So those circuits are actually, we are going to discuss one by one. So this is AND gate, OR gate, NAND gate, NOT gate, like that. Actually there are few gates which we can discuss. Got it? So you can note down this. Now actually we design the second one, OR gate. So in the OR gate, so for 2 different inputs of A and B, you are expecting an output of Y. It should be such that if any one is 1, then actually it should be 1. 0, 1, this is 1. 1, 0, this is 1. 1, 1, this is 1. So this is the basic functionality of an OR gate. So this is the OR gate. So here actually in one statement you can write as, if any one input is high, then the output is also high. Got it? So the terms actually high, true, 1, all are synonyms as far as Boolean algebra is concerned. And similarly, low, false, 0, all are one and the same. So this is represented with 1, this is represented with 0. So we can interchangeably use all these words. Got it? High, true, and 1. Low, false, and 0. Got it? So like this actually you can design an OR gate. Similarly, buffer. Buffer actually, it is going to be used for certain internal purpose of impedance matching, where the same output whatever you have given, right? So the same thing you will get as an output. So this is buffer. So if you give A here and again actually you will get A. So the truth table of this is, if you give 0, this is 0. If you give 1, this is 1. So this is a special gate where this is used for the impedance matching purpose. Got it? So no change. Whatever the input you give it, the same output you are going to get it. But actually, if you get a NOT gate actually, it is symbolized as 0 here. So this is a circle, you will get it. And this is what is called as the NOT gate. And this is the buffer. In the NOT gate, you will get an exactly opposite one. So if you give A here, and this is Y equal to A bar. So if you give 0, you will get 1. If you give 1, you will get 0. So this is the truth table of a NOT gate. So then next is exclusive OR gate. The exclusive OR gate, sometimes it is called as the XOR gate. So, or actually sometimes it is called as the XOR gate, like this. So this exclusive OR gate, so the statement actually, if an odd number of inputs are high, then the output will be high. If an odd number of inputs are high, then the output is high. And this is called as the exclusive OR gate. So here, in the XOR gate, this is A, and this is B, and this is Y. So if this is 0, and this is also 0, this will be 0, and this is 0 and this is 1, this will be 1. This is 1 and this is 0, this will be 1. This is 1, this is 1, this is 0. If you notice, here actually only 1 is there. 1 is an odd number, so 1 output. Here also 1. Here 2 1s are there, even number, so it will be 0. Here no 1s are there, it will be 0. Got it? So this is the exclusive OR gate. And the functionality here actually A bar B plus AB bar. So this is how you can realize this. If you notice A bar B meaning, so A bar means opposite of A. So this is also called as A prime. A bar or A prime. So whatever it may be. But it is meaning that opposite of it. Now A bar B. So A bar means, if I write it here, A bar so if I write A bar here and B bar here, so A bar is 1 1 0 0 and B bar is 1 0 1 0. So bar of this. So 0 becomes 1, 1 becomes 0, 0 becomes 1 and 1 becomes 0 here. And similarly 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0 here. Now here actually, if you notice, if you find out this value A bar B plus AB bar, so here A bar B, so A bar is 1 and B is 0. So here actually there is a dot. Dot means the product which is nothing but the AND gate. So AND gate actually 1 into 0 is 0 and A bar B, if you notice. Now and AB bar is A is 0, B bar is 1 and this is again 0. So 0 plus 0. So if you notice 0 plus 0, this is going to be 0. That's what we have written here. Similarly, if you take the second one, A bar B plus AB bar. A bar B value is 1.1. This is 1. So 1 plus anything is always 1. So this is 1. Now the third one, if you take it, so A bar B, A bar is 0, 0 times of 0 is 0 and AB bar, so B bar is 1 and A is 1. 1 dot 1 is 1. 1 plus anything is anyway 0. So that's why you can write 1 here. Similarly, the next one is 0, 0 here. Now A bar B, this is 0 dot 1. So 0 dot 1 and then 0 dot 1. So again it is 0 plus 0. So you are going to get 0 here. Got it? So whatever may be the number of inputs it is, you have to count for odd number of inputs has to be 1. Then only it will be 1. Otherwise it will be 0. This is how you can remember it. Got it? So here X, so next one is X NOR gate. So before that actually I will discuss NOR gate and NAND gate. NOR and NAND. So here the NOR gate is not OR. That is the meaning of NOR gate. So not OR means opposite of OR. So if you write the truth table A, B and then here actually if y is equal to A plus B or A or B, A plus B is the mathematical form to write A or B. So wherever R is there you can replace with plus and wherever AND is there you can replace with dot. So this is A plus B and then here actually X NOR, so this is R, X NOR gate is Y bar. Got it? Y bar means opposite of Y. R opposite. So Y bar. So this is 0, 0, 0, 1, 1, 0, 1, 1. So for OR gate this is 0, this is 1, this is 1, this is 1. And for NOR gate, X NOR gate, this is 1 and this is 0, this is 0 and this is 0. So this is the meaning of X NOR gate. So this can, you can even write as Y is equal to A plus B whole bar. Then next is NAND gate. NAND meaning not AND. So that is the NAND gate. So not AND. So this is the NAND meaning. Now if you write the output of, so here I will write Y is equal to A dot B, which is the AND, A and B. Then this is going to be, this is 0, this is 0 and this is 0 and this is 1. And not of this is 1, 1, 1 and 0. So this is the NAND gate. Got it? So now, so these are the basic gates or the fundamental gates we can call. So these are the truth tables of those fundamental gates. Now actually, I'll give you one more gate. So this is, I'll give you the symbols first. So this is the AND gate. So OR gate symbol is, there is a curve like this and then you can put like this and this is the output and this is the input. So A and B and this is A and this is B. Y equal to A plus B and Y is equal to A dot B. And similarly, NOT gate is, so this is A and this is Y is equal to A bar. And the NAND gate is, so there is a circle here for NAND gate. Y is equal to A dot B whole bar. NOR gate, there is a circle here. This is A and this is B, and Y is equal to A plus B whole bar. This is NAND gate, this is NOR gate. This is AND, OR, NOT, NAND, NOR. And exclusive OR gate is, so two curves are there. And here OR gate. So this is XOR gate. And this is A and this is B. Y is equal to A bar B plus AB bar. This is the exclusive OR gate. And XNOR gate is if you put a circle, then we call this as XNOR gate. And this is Y is equal to A bar B plus AB bar whole bar. So this is XNOR gate. So if you get an N, then opposite of it, that's all. Now actually, I will give you one circuit. See this. This is the NAND gate. Then actually what I have done is, I have connected these two and then actually I have given an input of A. Then what should be its output? Or you draw the truth table of it. What is the truth table of this? If I give you a single input to the NAND gate. What is Y value? So this is going to be A bar. So if I give the same input to both, then actually you are going to get exactly opposite of the input whatever we have given. So this is the beautiful feature of a NAND gate. And similarly, can you try to do for NOR gate also? So if I give A, then what is the value of Y? Anybody got the answer for this? So this is again A bar. Why? Because I'll write for the NAND gate. See this. So this is A. And this is also A. Earlier actually it used to be A and B. Now if I give 0 here, it will come 0 here. If I give 1 here, I will get 1 here. Now the output is the NAND gate output. NAND gate is not of AND. So not of AND is, see this, 0.0 is 1, 0.0 is 0 and opposite of that is 1. 1.1 is 1 and opposite to that is 0. So if you give 0, you are getting 1, if you give 1, you are getting 0. That is exactly the opposite functionality of the input. So similarly, even for the NOR gate also, it will be the same kind of truth table. So here, even if you give NOR gate A here and the output is NOR. If you note this, this is 0, this is 0, this is 1, this is also 1. Now for a NOR gate, not of R. Not of R means 0 plus 0 is 0 and opposite to that is 1. 1 plus 1 is 1 and opposite to that is 0. Now if you notice, this is again A bar. So this special kind of feature is there for these two gates. See this is not a rectangle. For the same gate, instead of A and B inputs, I have connected both the inputs and connected to a single input A. That means I am giving A for both the places. So then actually the output is going to be exactly opposite of what is the input given here, right? So Y is equal to A bar. Similarly, even for this one. Now here, these are the two gates actually, which has actually this beautiful functionality you can easily realize. Now, that's why these two gates are called as the basic building blocks. Why we call these two gates as the basic building blocks is, you can realize any kind of circuit of your own with the help of only these two gates. Whether it may be an AND gate or NAND gate or NOR gate or XOR gate or XNOR gate or NOT gate or any kind of gate can be constructed with the help of these two gates. That's why these two gates are called as the basic building blocks of any digital design. Got it? Now actually, let us construct an AND gate from here. So from the NAND gate, how can we construct an AND gate? I hope you noted down. So with the help of NAND gate, I wanted to construct an AND gate. See this. So this is the AND gate I want. Right? So with the help of NAND gates, what I will do is, I will put a circle here and I will put a circle here. So if I give here, so whatever the output for AND gate, it is going to be Y. Y bar whole bar. Y bar whole bar is again Y. That means this is the AND gate functionality. If I put two different circles and each circle meaning opposite. Now here, this can be, so this is an AND gate, NAND gate, and then this circle I can replace with a NOT gate like this. But actually, I wanted to construct only with the help of NAND gate. And NAND gate, NOT gate functionality we can realize with the help of this kind of connection. So this can be replaced with so this is the AND gate. Got it? So with the help of only NAND gates, I have constructed an AND gate. I hope it is understood. So we can construct with the NAND gates even the OR gate also. How can we construct? So for that actually, before proceeding on to that, let me introduce Boolean algebra. I hope it is noted. So these are the basic building blocks what we can make use to construct any bigger circuit of our own interest. So all the processors like actually i7 processor or i4, i5 or i3 processor or the cell phone processor, whatever it may be, everything is designed only with this kind of circuits. Got it? So these circuits are actually, now actually we have got the flexibility. These are the inputs available. This is the output expected. If you give that, we will be able to design the circuit inside. So for that actually we can make use of these building blocks, but how you are going to make use of these building blocks is decided by the Boolean algebra. Got it? So this Boolean algebra, now actually, so I wanted to construct with the help of NAND gate an OR gate. So the OR gate functionality is A plus B. So this is the OR gate functionality. Now for that actually what I will do is, I will put two different bars on top of it. So here a plus b whole bar can be written as a bar dot b bar whole bar. So how I have written? So these are the rules of Boolean algebra. Now let me define what is the Boolean algebra. So Boolean algebra is not like an arithmetic algebra. So this is a logical algebra. So any algebra is nothing but the set of rules to do certain mathematical activity. So that is the algebra. Now here logical algebra it is. So here actually for a plus actually there was a different meaning that was given in case of Boolean algebra, and for a dot actually there was a different meaning that was given, and then there is no negative sign or there is no division sign in case of logical algebra. So only plus and dot, and there is something called bar or prime, meaning opposite. So here actually plus meaning, so 1 plus 1, this has to be treated as 1. Why it has to be treated as, so this is not an arithmetic addition. So you might tempt with 1 plus 1 is equal to 1 0 in case of binary number system if you add it directly. But here this and this are nowhere related. So 1 plus 1 is equal to 1 for all practical purpose. So 1 plus 1 has to be treated as 1. Now here what it means for us is true or true, has to be true. This is the meaning of it, true or true. So that means suppose if I say this, if sir is there and students also there, then the class will happen. So both has to be there, and this is an AND operation. So both has to be true so that the class can happen. Suppose if anyone is present, then suppose actually whether the SAR comes or not, the institute will be open always. Right? So that is independent of the SAR. That means here actually an OR operator has to be there. If any one is true, then automatically it has to be true. So this one conveys a true. It's not the arithmetic one. Got it? One conveys true. And if 0, so exactly in the similar manner, 0 conveys that it has to be a false. So false or true is again true. False or false is a false. Got it? So this is how actually the Boolean algebra was built. So don't get confused with that. This is not an arithmetic operation. This is a Boolean algebra. Got it? And similarly 1 plus 0 is equal to 1. And 0 plus 1 is equal to 1. And 1 into 1 is equal to 1. And 0 into 0 is equal to 0. And 0 dot 1 equal to 1 dot 0 is equal to 0. These are the basic operations of Boolean algebra for plus and dot. Got it? And then bar, so suppose y is equal to a bar. So opposite of a. So a bar whole bar is equal to a. Why? Because opposite of opposite. Again it's the original. So a bar whole bar equal to a. Got it? So, and then these are the basic symbols what we are going to use it. And then there are certain basic theorems also. So those theorems actually I will discuss. First you note down this. Then, okay. So those theorems are the rules. So the first one is the commutative law. So commutative law, it means that if you interchange the positions, actually the meaning won't change. That is the meaning of a commutative law. So here a plus b equal to b plus a. So this is the commutative law. And similarly for the multiplication, a dot b is equal to b dot a. So even if you interchange the positions, then the result won't be changed. So this is the commutative law. And the second one is associative law. And this associative law says that a plus b plus c. That means here actually I have done b plus c first, and then actually I have added to a. It exactly gives the same result of if I add a plus b first and then c. It won't make any difference. Similarly for the multiplication also, a dot b dot c is equal to a dot b dot c. It won't make any difference. So this is associative law. And then the distributive law. So all these are actually the basic algebra of arithmetic. The same rules holds good even for the basic algebra also. But in case of distributive law, there is a little difference. So we know that a dot b plus c, this can be written as a dot b plus a dot c. So this is the distributive law. This rule also, it is at par with the normal algebra. But the difference is a plus b dot c. For this actually we cannot write a plus b dot a plus c. So that is a failure case in case of normal algebra. But here in case of Boolean algebra, this can write as a plus b times of a plus c. So this is different. This is applicable only for the Boolean algebra. So now actually let me prove this. So I take the right side and then try to prove this. See this, if I multiply these two, then this is going to be a dot a plus a dot c plus b dot a plus b dot c. Now here a dot a is a. This is identity rule. So I have to discuss that also. So as per the identity law, a dot a will always result into a. So plus if I take a common, then actually this is going to be b plus c plus b dot c. And then if I take a out of this, so this is going to be a times of 1 plus b plus c plus b dot c. And there is one more rule. If 1 plus anything comes, it is always 1, because 1 2 is there. So addition of or of anything, either it may be a true or false, it is always true. So 1 plus anything is always leads to 1. So this can be treated as 1, and a dot 1 is equal to, so rules whatever I have used is a dot a is equal to a, and a dot 1 is equal to a, and 1 plus x is always 1. So these are the rules actually I have used in deriving that. Now here 1 plus of anything is always 1, so this can be treated as a plus of b dot c. Now if you notice, this is the left hand side. So though it is a failure in case of normal algebra, this is valid in case of Boolean algebra. A plus of b dot c can be written as a plus b dot a plus c. Got it? So these are called as the identity laws. I hope you noted down this. Identity rules. A dot 1 equal to 1 dot a is equal to a. and a plus 0 is equal to 0 plus a is equal to a. So even if you add a 0, it won't make any difference to the value. Even if you multiply with 1, it won't make any difference to a. Got it? So this is the identity rule. And complementation rule. So these complementation rules are pretty straightforward. A plus a bar always leads to 1. This is always 1. And a dot a bar is always 0. So these are the basic rules. So along with the basic understanding or the definitions of the Boolean algebra, with these laws whatever we have discussed, we should be able to solve all kind of complex Boolean expressions. Got it? And there is one more important rule, that is De Morgan's principle. So this is very important principle, De Morgan's principle. So this De Morgan's principle, what it says is a dot b whole bar can be written as a bar plus b bar. And similarly, a plus b whole bar can be written as a bar dot b bar. So this is the De Morgan's principle. So this is very highly used principle actually. So most of the simplifications will be done with the help of this De Morgan's principle. Got it? Any questions on this? So this you can verify or the cross check with the normal methodology, that is AB and then a dot b whole bar, and here a bar and b bar, and then here a bar plus b bar. If I take it, these two has to match, right? A dot b whole bar has to be equal to a bar dot b bar. Now if I take the inputs as 0 0 0 1 1 0 and 1 1, these are the inputs. Now the corresponding outputs will be, so NAND gate. So NAND gate is 0 dot 0 opposite of it. So that is 1, and 0 dot 1 is 0. 0 opposite is 1, and this is 1, and this is 0. Similarly, a bar is 1 1 0 0, and similarly here 1 0 1 0, and a bar plus b bar. So if you add these two, this is going to be 1, this is 1, and this is 1, this is 0. If you notice, this one and this one are one and the same. So this was the rule stated by De Morgan. Similarly, you can verify this. A plus b whole bar has to be equal to a bar dot b bar. So if I put it here, a plus b whole bar. So a plus b whole bar is 0 plus 0 is 0, and bar is 1, and 0 plus 1 is 1, bar is 0, and this is 0, and this is also 0. And similarly, a plus b whole bar should be equal to a bar dot b bar. So here a bar dot b bar, if I put it here, so 1 dot 1 is 1, and 1 dot 0, 0 dot 1, 0 dot 0, all are zeros. If you notice, these two are one and the same. So these are the two important rules of De Morgan. Then, so now actually the types of functions. So types of Boolean functions actually or actually this is also called as the normal forms. So normal forms So what this normal form says is you wanted to realize any particular function. So for that actually what you will do is let us say AB, and then actually I randomly want this has to be 0, 0, 0, 0, 1, 1, 0 and 1, 1. Let us say this has to be 0 and this has to be 1 and this has to be 0 and this has to be 1. And this is the kind of output actually I am expecting. And then actually for that I wanted a digital design. So for that what I need to do is, here there is a concept of normal forms. Normal forms actually there are two different types of normal forms. One is DNF. So this is disjunctive normal form. Disjunctive normal form. And then CNF, this is conjunctive normal form. So don't get confused with these terms. These are very, very simple terms. See this, here normal form actually, so this DNF means, so sum of products. And this is called as product of sums. So DNF is called as the sum of products and CNF is called as the product of the sum. Now here the sum of the products, product of, so here actually there is something called min term. Min term meaning here actually you are getting 1, and for this one 0 has to be input and 1 has to be input for A and B. So if you want to get 1 here, I can construct an AND gate with the inputs of A bar dot B. And similarly, if I have to get 1 here, I have to construct A dot B. Got it? So this is A dot B and this is A bar dot B. Now if I construct an output A bar B plus AB, and this is the output actually I can get it. Got it? So this is one min term and this is one min term. Min term meaning minimum term. That is the meaning of it. Minimum term. So min term. So max term. So here actually product of sum is the max terms are used. Now to construct the same thing, here actually I can construct this as, see this, so wherever 0 is there, so you talk with the 0. Now this can be written as A bar plus B bar, and this can be written as, where you are getting 0, this is A plus B bar. Now this can be written as Y is equal to A bar plus B bar dot A B bar, A plus B bar. And this is called as the CNF and this is called as the DNF. That is the difference. Got it? So wherever the ones are there, you are using those ones to construct the Boolean function so that you can expect the resultant output what you are required, right? And similarly, this can be done with the help of this one where you are expecting zeros with the help of plus. And plus terms are called as the max terms and dot terms are called as the min term. And this expression, entire expression, is one form called as the Boolean form, and this is the DNF form or disjunctive normal form, and this is the conjunctive normal form. So whatever may be the number of inputs it is, so you have to worry about only the outputs. Wherever the outputs are 1, you construct a min term there and then add all the min terms together so that you can get the resultant output there. Yeah, this has to be 1. So 1 plus 0, right? So this is 1 and this is 1. So 1 plus 1 is 1. So this is 1 and this is 1. Now here actually what you are constructing is Y bar you will construct from there. Yeah, so this is Y bar. y bar you will construct, and from there actually you will try to construct the y value. Got it? Understood, Pankaj? Yeah. So here, whether you are using ones or zeros, ones implies DNF. And here zeros are used. Now here actually once you get this kind of function, then actually from this actually you will try to simplify this. So this is, if you notice, this is a bar b plus ab, and then b, if you take it out, a bar plus a, and a bar plus a is 1, this is going to be b. Right? If you notice, see here, this is 1 and this is 1. So whatever the b input is there, that is the output you are expecting. Then why to worry about a? And that simplification will be done with the help of the Boolean algebra, which results in y equal to b rather than y is equal to a bar b plus ab. So this is the advantage of Boolean algebra. So if you are expecting this kind of output, then actually if you don't know this Boolean algebra, we should be worrying about both a and b. But actually with the help of this DNF and CNF forms, you constructed a Boolean expression which you are able to simplify it to a normal form, which is very, very simplest form, and this is coming out to be b. Then actually for the user, right, you can directly suggest that don't worry about a and ignore a and try to take the output as b directly itself, and that will be your design. So this is the most simplest, but actually in reality you might expect thousands of inputs. From there actually you have to construct these outputs with the help of the functions. There actually this complex level of Boolean algebra will be dealt in a much more regressive way. Got it? Understood? Normal forms, any questions? So this is the brief history about the Boolean algebra. If you have any questions, you can let me know. So you can make use of these expressions to simplify any complex level of Boolean expressions. Yeah. So if no other questions, I'm going to stop the class for today. In the next class, I'm going to, so I think, so one last thing actually, this one, the NAND gate construction, I will explain that and close it. Now if you want to construct a plus b with the help of NAND gates, for that what I will do, I'll put two different bars. So this can be called as a bar dot b bar whole bar. So this is as per the De Morgan's principle. As per the De Morgan's principle, I have just written a plus b whole bar can be written as a bar dot b bar. And then, so this I will realize a bar dot b bar, so it is so this is A and this is B, and two different circles implies A bar and B bar. And then for that actually, so this is A bar dot B bar whole bar. Got it? And this itself is a NAND gate. And these NOT gates you can construct with the help of NAND gate again. So that is so this is as if like y is equal to a plus b. Now if you notice, I have constructed only with the help of NAND gates. Got it? So any gate can be constructed with the help of NAND gate, and any gate can be constructed with the help of NOR gate also. So that's why these two are called as the basic building blocks. So as you are able to construct any kind of gate, then any complex level of design can be built with only with the help of NAND gate or NOT gates. Got it? So for this construction, you are making use of the Boolean algebra. Okay, yeah. So that's all for today. In the next class, I am going to deal with the computer peripherals and the memory. Yeah, thank you. Good night.